Alan Turing, Alonzo Church, Claude Shannon, John von Neumann, Kline, and Kurt Gödel. What is a common thing for all these great mathematicians? It's theory of computation. All these people have greatly contributed to the theoretical computer science, and their contributions have a huge impact on the field. If you have ever used a computer, the fact is, you have definitely used some form of application which relies on their mathematical contributions. Theory of computer science is the theoretical representation of computers and their applications. TOC in a nutshell. Let's take a quick overview of theory of computation, also called as TOC. I usually refer to theory of computation as TOC from now onwards. TOC can be divided into four major categories. Each category has its own representation, application, and limitations. The four categories are regular grammars, context-free grammars, context-sensitive grammars, and recursively enumerable grammars. All these four grammars fall under the category called generators. So, a grammar is used to generate input strings based on a set of rules. Each problem statement will have a separate set of grammar rules. So, if we want to solve a problem, then we need to devise our own grammar and generate the input strings. But where does this grammar come into picture, and where does the input generated by this grammar go, and how this input is consumed? There comes the automaton. For all the generators, we will have acceptors. So a grammar, and to process that grammar, we will have automaton. We have four types of automaton, one each for every grammar. Regular grammars will be processed by finite automaton. I mean to say, the input generated by the regular grammars are processed by finite automaton. Input strings generated by context-free grammars are processed by push-down automaton. Input strings generated by context-sensitive grammars are processed by linearly bounded automaton. And finally, recursively enumerable grammars, and they are processed by Turing machines. To reiterate, we have four types of grammars. They are regular grammar, context-free grammar, context-sensitive grammar, and recursively enumerable grammar. Now, let us see about the automaton in a more detail. For regular grammar, we have finite automaton. It has a limited power as it does not have any memory component for processing the inputs. So, the finite automaton is mainly used in the fields of string processing, network protocol designing, bot designing, system designing, or Boolean expressions analyzer. And we will mostly see the finite automaton applications in game designing as well. If you are playing a game and it is having some kind of state based movement, then the thing is it is using finite automaton. The acceptor for a CFL or context-free language is push-down automaton. It is more powerful compared to finite automaton. It has a stack, which is the memory component, which can be used to process the input strings. If you see, it is also having a finite automaton, and the input is provided on a tape, and along with these two, it is having a stack to store some information. This gives more power to push-down automaton compared to finite automaton. Linear bounded automaton. It is the acceptor for context-sensitive grammars. This has a bounded read-write memory component which will be used to process the input strings. The input tape has a limited memory, but the read-write capability makes this automaton more powerful compared to push-down automaton. In push-down automaton case, it cannot read and write onto the both onto the same input tape. It can just read the input, but writing is onto another stack. But in case of linear bounded automaton, we have a bounded memory. The memory is the starting and ending of the memory is represented by a dollar symbol, and the whatever memory available in between these two dollar symbols, in between these two endpoints, is available for reading and writing the input and output data. Even this uses a finite state automaton. So basically a finite automaton is the base for all these remaining automaton. These all leverage finite automaton, and due to the memory component and its capabilities, they have different powers. And finally comes the all-powerful Turing machine. It is considered to be equivalent to the modern day computer with all the computational power as it is. So a Turing machine can perform all the operations that a modern computer can perform. It's like it is not actually the GUI point from a GUI point of view, but from a computational power point of view. If your computer is able to calculate a complex number multiplication, yes, Turing machine is able to do that. If your computer is able to perform a sorting algorithm, yes, Turing machine can do that. If your computer is trying to perform some complex scientific calculations, yes, Turing machine can do. Whatever our computers are able to do, Turing machines can do, except from a GUI point of view, because these all are mathematical models. These are not actual implementations of, these are not actual hardware implementations. These are all conceptual things in the form of mathematics. So all the automaton use the FSA, as I have already mentioned, as a processing machine for state transitions, output generation, and etc. So understanding the finite state automaton is a basic for TOC. Without being able to represent a problem mathematically using the FSA, you will not be able to create a correct mathematical model for your problem. Where does TOC be useful mostly? If you want to model a system and validate it even before building the system, you need TOC. To understand the possible states the system can be in and handle the input and output accordingly, you need TOC. To understand the resource consumption of a system for a given problem, you need TOC. For any kind of AI enabled gaming, you will definitely use some form of TOC concept. Machine learning, yes, it does use TOC. And natural language processing, it will definitely use TOC. So if you see all the major areas in computer science, computer networks, machine learning, artificial intelligence, game development, app development, touch or talk about anything in computer science, it does use TOC. So let us see about TOC, and we shall start with finite automaton and regular grammars in the first module.